Hello, this is Rama Krishna from KL University delivering series of lectures on heat transfer. In continuation of our lesson number 3 related to three-dimensional conduction heat equation in Cartesian system, we will proceed now further to the derivation of three-dimensional conduction heat equation in cylindrical and spherical coordinate systems. So at the end of this session, you will be able to understand what is polar coordinate system and what is spherical coordinate system, and what is the importance of polar and spherical coordinate system in heat transfer analysis, how to consider a three-dimensional element in cylindrical and spherical systems, and how to apply the same energy conservation principle to a three-dimensional element in cylindrical and spherical systems, and how complex a real heat transfer problem is. In general, when you consider a slab, we choose the dimensions x, y, and z because we can measure it in terms of x, y, and z coordinate system. But whereas when it comes to a cylinder, the conventional system followed is r, theta, z. For example, consider a radius r. Rotate this radius r 360 degrees. You develop a circle. So that means when r is taken an angle theta equal to 360 degrees, you develop a circle. Go on keeping circles one above the other in z direction, it builds a cylinder. So the general system of representing a cylinder is not in xyz but in r, theta, z coordinate system. That r, theta, z coordinate system is called polar coordinate system. Most of the heat transfer applications fall under the category of coordinate, cylindrical or polar coordinate system, because any heat exchangers or any equipment will have the fluid flowing through a pipe. Pipe is nothing but a cylindrical one. So the coordinates of that pipe are best specified in terms of polar coordinates rather than linear x, y, z. But anyhow, when the radius is too high, few scientists approximate it as a cubical element and consider it. That is another issue we will see later. That approximate method we will see later. So now, time being, when we consider a cylindrical element or in polar coordinate system r, theta, z, how to apply the energy conservation principle to this and derive the conduction heat equation. From the origin, let us consider a distance r subtending an angle d theta. So you develop an arc of r d theta length. The length of this arc is r d theta. You can see. And in the radial direction, take a thickness of the element equal to dr. So the radius up to this point from origin O is r, and the radius up to this point is r plus dr. And the subtended angle of this arc is d theta. So the length of the arc is r d theta. We consider this dr very, very small, such that the length of the arc even after distance dr is still equal to r d theta. Strictly speaking, it should be r plus dr into d theta, but dr is very, very small, so we take r plus dr is approximately equal to r. Now in the z direction we consider the depth of the element as a dz. So now it is a three-dimensional cylindrical element having dimensions in radial direction dr, in theta direction a dimension of r d theta, and in z direction a height of dz. Therefore, the volume of this element is r d theta into dr into dz. That is the volume. Suppose the density is say rho, mass of the element is rho into dr into r d theta into dz. Now like in Cartesian system, here also we will consider the heat transfer in all the possible three directions, three-dimensional. Let heat entering in the radial direction is QR. Please look at this arrow. The heat entering in the radial direction is QR, and heat leaving in radial direction at a dimension r plus dr is say q at r plus dr. Similarly, the heat entering in theta direction is say q theta, and the heat leaving at theta plus d theta is q at theta plus d theta. Similarly, the heat entering in z direction qz, and the heat leaving is say q z plus dz. As it is, if you consider the energy balance, the heat entering in three directions should be equal to heat leaving in three directions. That is qr plus q theta plus qz equal to qr plus dr plus q theta plus d theta and plus qz plus dz. However, this solid element is having some specific heat and is supposed to have a mass m. Therefore, it stores or holds some amount of energy by virtue of its rise in temperature because of this heat transfer. Let the amount of energy stored by this element is mcp dt by d small t, where small t represents time, the rate of energy storage. So, energy entering into the element is equal to energy stored in it plus energy leaving. You understand? Again I will repeat. Energy entering into the element is equal to energy leaving from the element plus the amount of energy stored in it. And let us assume, as specified in the last class, there could be a chemical reaction going on, or the electrical resistance causes some amount of heat generation, or there could be nuclear fission or fusion reaction going on. So because of all these, let us assume there is an internal heat generation per unit volume as Qz or Q. So there is a total internal heat generation of Q into volume, that is dr into r d theta into dz. So when you consider the internal generation of heat energy within this element, then the energy balance equation can be written as the energy entering into the element plus energy generated within the element is equal to energy leaving from the element plus energy stored in the element. I hope I am clear. Energy entering plus energy generated equal to energy leaving plus the energy stored in the element. So Now, coming to the Fourier conduction equation, QR is equal to minus Ka dt by dx. Here the area is area normal to the radial direction. Carefully observe here. In the radial direction, heat is going as shown by this arrow, QR. Look at the pointer. So to this QR, the area normal to the direction is this area, this face, having r d theta length, height dz. So the area is r d theta into dz. Thickness in the direction of heat flow is dr. Therefore, we can write the equation QR equal to minus K area r d theta into dz dou t by thickness in radial direction dou r. Similarly, the heat transfer in theta direction is minus K area normal to the theta direction. This is the theta direction, heat leaving in theta direction. Normal to this theta direction, the area is this face area. This face area is height dz and width dr. So therefore the face area is dr into dz. And in theta direction, equation is minus K dr dz into dou t by thickness is r dou theta. In z direction, qz equal to minus K area normal to that r d theta dr into dou t by dou z. Here I have not considered kr, k theta, kz. I am assuming kr is equal to k theta equal to kz, an isotropic material. Directly I have written the equation in this form. Considering the mathematical approximation, the heat leaving at r plus dr is equal to rate of change of QR per unit thickness into total thickness will give you the total change plus original QR will give you the heat leaving at r plus dr. So QR plus dr is equal to QR plus dou by dou r of QR over a thickness of the element dr. Similarly, Q at theta that Q theta over a thickness of r dou theta. So per unit change, what is the increment in Q theta? That is dou Q theta by r dou theta. And for a overall thickness of r d theta, what is the total change plus the original value Q theta will give you the final value. So Q theta plus d theta is equal to Q theta plus dou by r to r d theta. In the same way, Qz plus dz is equal to Qz plus dou by dou z of Qz into dz. Students are advised to concentrate more on the second term carefully. Now applying the energy balance, the heat entering into the element plus the amount of heat generated internally is equal to the heat leaving from the element and the rate of change of energy in the element or accumulation of energy within the element. So when you substitute QR plus Q theta plus Qz plus Qz, that is the amount of heat generated per unit volume into volume of the element r d theta dr dz equal to heat leaving qr plus dr plus q theta plus d theta plus qz plus dg plus rate of change of energy mc p dt by dt. Now when you have qr on left hand side and qr plus dr on the right hand side, and when you expand qr plus dr and substitute qr plus dou by dou r of qr dr, the right hand side qr and left hand side qr cancels, and minus dou by dou r of qr into dr will come to the left hand side. And similarly, minus dou by r dou theta of q theta r d theta will come to the left hand side. And similarly, minus dou by dou z of qz dz will come to the left hand side. Plus internal heat generation qz r d theta dr dz equal to mc dt by dt or rho dr d theta dz dou capital T by dou small t. In fact, total derivative is wrong, partial derivative. Now coming to this one, minus dou by dou r of qr is minus k r d theta dz dou t by dou r dr. So if you look at this term, we are taking this derivative with respect to r. So r is a variable and dou t by dou r is also a variable. In terms of partial differentiation, this k d theta dz can be brought outside. So we are left with dou by dou r of r outside because we have to take it as a variable while differentiating with respect to r. In this term, dou by r d theta minus k dr dz, you are finding out the derivative of this term with respect to theta. Hence, k dr dz by r can be brought outside the term. You have only dou by dou theta of dou t by dou theta. Similarly, dou by dou z of dou t by dou z and qz r theta dr dz, etc. So, by bringing out this d theta dz dr, d theta dz dr, d theta dr dz, the term dz is missing here. You can cancel that and you will get ultimately dou by dou r of kr dou t by dou r plus dou by r d theta of k dou t by r dou theta into r, dou by dou z of k dou t by dou z into r plus qz into r equal to rho cr dou t by dou small t. So now take k also common and differentiate it. You will get r dou square t by dou r square plus dou t by dou r into dou by dou r of r is 1. Applying UV rule, you will get these two terms for the first one. And the second one is k by r dou square t by dou theta square. And the third one is kr dou square t by dou z square plus qzr equal rho cr dou t by dou t. And dividing with r, you will get dou square t by dou r square plus 1 by r dou t by dou r plus 1 by r square dou square t by dou theta square plus dou square t by dou z square plus qz by k is equal to rho c by k into dou t by dou small t. If you consider one-dimensional conduction heat equation in cylindrical coordinate system without internal heat generation under steady state. Under steady state, dou t by dou small t becomes 0. Without internal heat generation, qz by k becomes 0. One-dimensional, only radial direction, neglecting the heat in theta and z directions, These two terms also vanishes. You will get ultimately dou square T by dou R square plus 1 by R dou T by dou R equal to 0. This can be written as dou by dou R of R dou T by dou R equal to 0. This is the one-dimensional conduction equation in polar coordinate system without internal heat generation under steady state condition. If you want to consider the unsteady state, you have to add this term rho c by k dou capital T by dou small t. And already we have seen k by rho c is called thermal diffusivity, which represents the capacity of the system to diffuse heat transfer. More the thermal diffusivity, at a faster rate, heat spreads in the solid. If you consider one-dimensional conduction heat transfer under steady state with internal heat generation, the equation will be dou square T by dou R square plus 1 by R dou T by dou R plus Qz by K equal to 0. So solution of these equations, depending upon the situation, you have to choose and solve. If it is a one-dimensional conduction heat equation as specified here without internal heat generation under steady state condition, it requires two boundary conditions to solve the problem. If it is one-dimensional with under unsteady state condition, then it requires two boundary conditions and one initial condition to solve the problem. As it is, if you consider a three-dimensional unsteady state problem, you need 6 boundary conditions and one initial condition to solve the equation. So this is the three-dimensional conduction equation in cylindrical coordinate system, the most useful in the analysis of heat transfer and in particularly heat exchanger applications. Radial systems are more common. Similarly, we can also try it for three-dimensional conduction equation in spherical coordinate system. You can observe slightly when compared to the Cartesian system, understanding the polar coordinate system is slightly difficult, and the spherical coordinate system is little more difficult. So you should possess the imagination to predict the element in a three-dimensional conduction spherical coordinate system. A sphere is developed first by rotating a radius r an angle of 360 degrees. You take radius r, rotate it 360 degrees, you develop a circle. Imagine that circle as a 1 rupee coin. Keep it vertically, 1 rupee coin on the table and tap it. It rotates on the table about its vertical axis, and you can visualize the shape of sphere. So that means initially you have taken a radius r, rotated in theta direction, you got a circle, and this circle again with reference to its vertical axis is rotated, spinned around its vertical axis to develop a sphere. So again an angle phi came into picture. So a spherical coordinate system is specified by r theta phi. A radius r, maybe say this one, rotated in theta direction, develops a circle, and again that is developed about this vertical axis, rotated in phi direction to generate a sphere. So let the distance from O to here is r. You are considering an element of d theta, so the length of this element becomes r d theta. And then see, this is r and the angle is theta. The projection length is r sin theta. And hence the length of this line where you are considering a piece is equal to r sin theta subtending an angle phi, d phi. So this arc length is r sin theta d phi. So one is r sin theta d phi, the other one is dr, and the third one is r d theta. Just consider a piece of water lemon. Imagine water lemon in spherical shape. To check whether it is properly ripened or not, we cut a small piece from its periphery. That is this one. You can observe here, this is the radial direction QR, and this is leaving QR plus dr at a distance of dr, and this is the heat entering in theta direction Q theta, and heat leaving at a distance of r sin theta d phi is say Q at theta plus d theta, and this is the heat entering in Q phi direction, and the heat leaving is at Q phi plus d phi. I will come again. The dimensions of this three-dimensional spherical element are, one is dr, the other one is r d theta, and the perpendicular one is r sin theta d phi. So volume of the element is dr into r d theta into r sin theta d phi. If you consider the density of the element as rho, mass of the element is density into volume, rho into dr into r d theta multiplied with r sin theta d phi. As it is, if you consider the energy balance for this, the energy entering is equal to energy leaving QR plus Q phi plus Q theta is equal to QR plus dr plus Q phi plus d phi plus Q theta plus d theta. Theta vector is going into the paper and coming out of the paper perpendicular to it. Let the element is having a specific heat C. So by virtue of its specific heat, when it is subjected to a change in temperature due to these heat interactions, it can store some amount of heat energy in it. The amount of heat energy stored in it is mCp delta T, and the rate of energy stored is mc delta T or dt by d small t, where small t represents time, rate of change of temperature with respect to time. Then the energy balance equation is energy entering is equal to energy leaving plus energy stored in the element. If you have some internal heat generation, then the energy balance equation changes to energy entering plus internal heat generated within the element is equal to energy leaving plus energy stored in it. Now let us write the expressions for conduction heat transfer in radial direction, theta direction and phi direction. In the radial direction, according to Fourier law, QR equal to minus Ka dt by dx. Here dt by thickness is dr. And the area A is normal to the direction of heat flow, that is this phase, having an area equal to r sin theta d phi into r d theta. Therefore, you can say that heat entering in r direction is minus k r d theta into r sin theta d phi into dou t by dou r. Small correction, dou t by dou r. And heat entering in theta direction is minus Ka dou t by the thickness in theta direction is r sin theta d phi. And area normal to the direction of heat flow, that is this phase area, which is equal to r d theta into dr. Hence, q theta is equal to minus k dr r sin theta d phi into dou t by thickness is r dou theta. Similarly, the heat entering in phi direction is q phi is equal to minus k dr r d theta into dou t by thickness in phi direction is r sin theta dou phi. And heat leaving in r direction is mathematically expressed as qr plus dr is equal to qr plus dou by dou r of qr into dr. And similarly, heat leaving in theta direction is q theta plus dou by r dou theta of q theta into r d theta. Heat leaving in phi direction is q phi plus d phi is equal to q phi plus dou by the thickness r sin theta dou phi into q phi into r sin theta dou phi. So dou of q phi by r sin theta dou phi gives you rate of change of heat in phi direction per unit length into over a length of r sin theta d phi total variation plus original q phi will give you the heat leaving at q phi plus d phi. And heat generated by the volume is qz into total volume is dr r d theta r sin theta d phi. Now writing the energy balance equation, we have heat entering into the element plus internal heat generation is equal to heat leaving from the element and heat accumulation rate within the element. So by substitution we get minus dou by dou r of qr into dou r minus dou by r d theta q theta into r d theta minus dou by r sin theta dou phi into q phi into r sin theta dou phi plus internal heat generation per unit volume qz into total volume r dr r d theta r sin theta d phi is equal to mass into specific heat into rate of change of temperature with respect to time. So upon simplification you will get 1 by r square dou by dou r of r square dou t by dou r into dr plus 1 by r square sin theta dou by dou theta of sin theta into dou t by dou theta plus 1 by r square sin square theta into dou by dou phi of dou t by dou phi plus qz by k equal to 1 by alpha dou t by dou small t. 1 by alpha is again rho c by k. So if you consider a one-dimensional conduction heat transfer in spherical coordinate system under steady state condition. Under steady state, dou T by dou T becomes 0. Without internal heat generation, QZ becomes 0. One dimensional, no theta term and no phi term, only radial direction. The equation simplifies to 1 by r square dou by dou r of r square into dou T by dou r equal to 0. This is the one-dimensional conduction heat equation in spherical coordinate system without internal heat generation under steady state. Solution of this equation will result in temperature distribution within the sphere as a function of radius. So in general, based on the three-dimensional conduction equation developed for Cartesian, cylindrical and spherical coordinate system, when it is considered as only one-dimensional with internal heat generation under unsteady state, for all these three, spherical, cylindrical and Cartesian system, the equation can be written in a generalized form as 1 by r power n dou by dou r of r power n into k dou T by dou r plus qz equal to rho c dou T by dou T. When n is equal to 0, the equation is applicable for Cartesian system. If n is 1, this equation is applicable for cylindrical system. If you substitute n equal to 2, then it is applicable for spherical system. N equal to 0, r power 0, 1, r power 0, 1, you will get simply dou by dou r of k dou T by dou r. So that is dou square T by dou r square. Instead of r, x direction, only one dimensional, you will get dou square T by dou x square plus qz by k equal to rho c by k dou T by dou T. That is for Cartesian system. Put n equal to 1, you will get 1 by r dou by dou r of r dou T by dou r plus qz by k equal to rho c dou T by dou T by k. That is what we have derived for one-dimensional conduction equation for radial system. Similarly, if you substitute n equal to 2, you will get the first term 1 by r square dou by dou r of r square dou T by dou r into dr, and then qz by k equal to 1 by alpha dou T by dou small. That's all about the three-dimensional conduction heat equation in cylindrical and spherical coordinate system. Now let us have some review questions. To test your knowledge, try to answer these questions. Earlier we have asked 7 questions, and now the review question starts from 8 onwards in this particular session. Is heat transfer a scalar or vector quantity? Explain. And question number 9. Consider a cold canned drink left on a dinner table. Would you model the heat transfer to the drink as 1, 2 or 3-dimensional? Would the heat transfer be steady or transient? Which coordinate system, that means Cartesian, cylindrical or spherical, would you use to analyze this heat transfer problem, and where would you place the origin? Explain. Question number 10. Consider a round potato like a sphere being baked in an oven. Would you model the heat transfer to the potato as 1, 2 or 3-dimensional? Would the heat transfer be steady or transient? Which coordinate system you prefer to solve this problem, and where would you place the origin? Explain. Now question number 11. From heat transfer point of view, what is the difference between isotropic and anisotropic materials? Question number 12. What is a boundary condition? And how many boundary conditions do we need to specify for a two-dimensional heat conduction problem? Question number 13. What is an initial condition, and how many initial conditions do we need to specify for a two-dimensional heat conduction problem, of course under unsteady state? Question number 14. Why do we try to avoid the radiation boundary condition in heat transfer analysis? Most of these questions from 9 to 14 are to test your mathematical ability. If you are thorough with partial differential equations, probably you would be able to answer these questions 9 to 15. Otherwise, brush up your mathematical knowledge and then try to answer these questions on your own. Then question number 15. What is heat generation? Give some examples. In the derivation of three-dimensional conduction equation, whether it is in Cartesian, cylindrical or spherical system, we have considered some amount of heat generation within the element. What is this heat generation? When do you experience? Give some examples. Next, last question for this. An iron is left unattended and box is left unattended, and its base temperature rises as a result of resistance heating inside. When will the rate of heat generation inside the iron box be equal to the rate of heat loss from the iron? It's related to the law of conservation of energy. Try to answer these questions. Otherwise, maybe in the foregoing sessions at the end, you will find the answers for these questions. Now to the review questions which are posed in the last session from 1 to 7. The answers are given here. These are all concept questions. One can understand very easily. Just go through these answers, keeping aside the questions which have been asked. You will understand them clearly. Now again, I advise you to go through these books. Maybe first chapter in all these books will help you to gain more and more knowledge on basics of conduction, convection and radiation, and the derivation of three-dimensional conduction heat equation. Thank you.